Yeah.
Okay, welcome PCS members to our today's PCS IBS seminar. It is a great pleasure to host today Professor Alexey Ustinov from Karlsruhe Institute of Technology in Germany. And our scientific host today is Sergey, and I ask you, Sergey, to introduce our speaker.
Okay, thanks, Steve. Welcome, everyone. And it's a great pleasure to have a short visitor with us, Alexey Ustinov, who actually was visiting PCS for its inauguration workshop, which will happen, I don't remember, was a long time.
8 years ago.
8 years ago, roughly. And now he is, so to say, on a longer trip to Asia, and we are very glad that he had time to stop by. He will give 2 talks, one today, one tomorrow. And he will also stay here, I think, for some time on Friday for those of you who want to chat more with him. Let me say a few facts from Alexey's biography. He did his Master of Sciences at the Moscow University of Physics and Technology, and in '84, and then in '87 he obtained his PhD in physics at the Institute of Solid-State Physics, also I think in Moscow, or Chernogolovka, I guess, or say. And then also obtained from the same place the Doctor of Sciences, which is the analog, say, of those who know what the habilitation is in Germany, just in a high degree, in 1995. Then in 1996, he moved to Germany, where he was a professor of experimental physics at the University of Erlangen-Nuremberg. And then he moved in 2008 to full professor position at the Karlsruhe Institute of Technology, or simply KIT, in Germany, where he is since running a big experimental laboratory, doing nice experiments. And I guess we will learn today about and tomorrow about some of them. He has published his main, maybe I should say, his main scientific interests are superconductivity, Josephson physics, microscopic coherence, quantum computing, perhaps, microwave spectroscopy, and so on. And he has published many papers. And it's very interesting that somewhere he lists here the 10 most important publications, and one which also has both of us as co-authors on it is among this list. And this is not the reason why we invited you here, obviously, but it's nice to remember this time when we worked together on some issues in the late 1990s and early 2000s. Okay, enough of blathering around. Alexey, please, the floor is yours. Let's welcome the speaker.
Thank you, Sergey, for hosting me here, for the invitation to give these talks. Okay,
can you move to that side?
To that side?
Yeah, the camera.
The microphone is not here, or?
Yes, it will work.
I would like to tell today about a really new work, which is not published yet. It has been shortly presented at the EPS March meeting by my former PhD student, now postdoc, Micha Wintermuth. It was just presented less than a month ago. And actually, it has to do with a hobby, which kind of field which I've not been working for quite a long time, almost 20 years, on the field of long Josephson junctions. So before I start with this topic, which of course is will contain some unpublished results, and it's not Polish presentation, so I really would welcome discussion, open questions. Please interrupt me if you want to ask the question on the way. Before I start, I want to say a few words about the place I'm coming from. So it's a Karlsruhe Institute of Technology. You see this custom center of Karlsruhe here. This is actually in the southwest of Germany, only about 15 kilometers from French border, near Palatine, and the town is in Baden-Württemberg. The place actually has been a university for a long time, and I was hired in this university in 2008. But in 2009, it was actually changed name, and there was a merge of the university with the former nuclear research center of Helmholtz Society. So the university exists for almost 200 years, and this is actually former Polytechnical College and then Technical University, Karlsruhe. And then the research entity of Helmholtz Society has changed to research center. It's not nuclear research center already for a long time, but actually it belongs not to the state, but to the society which manages large experiments like DAISY and ULIC and so forth. And basically it became, to my knowledge, the largest research education organization in Europe, with the annual budget almost getting close to 1 billion euro. So the university actually is located in the very center of the city, and the research center is only 10 kilometers north across the forest, and there are labs in both places. Therefore, actually, in the list of authors, you've seen 2 affiliations. So most of us actually belong to 2 institutes, one in the south campus and the other one in the north campus. Okay, this is basically what the university does research, education, and innovation. And in my group, we are working at the south campus mainly on the field which Sergey already mentioned. So this is superconducting circuits, superconducting devices. We work on superconducting qubits, quantum simulators, experimental implementation of quantum computing components, quantum metamaterials. This will be related to the topic of my talk tomorrow. Quantum phase slips. And the group is actually in the qubit community is very well known for the topic which is not being discussed today. This is 2-level defects in qubits. We are getting very generous funding from Google for doing this research, studying the origin of coherence, the coherence actually in superconducting circuits. And the subject of my talk today is, as I mentioned already, is fluxes, in particular quantum fluxes. So that's something which maybe not everybody knows immediately. So I want to start with some rather general introduction into the subject, and then show you very fresh, very new data, which we find very exciting. So imagine you have a Josephson junction, which is extended in the plane of the tunnel bed. So it's a junction which is distributed. That means that the phase difference of the junction depends not only on time, but also depends on the coordinate along the junction. So in this case, if the junction has a size comparable with the Josephson penetration depths, or larger than the Josephson penetration depths, it can accommodate Josephson vortices. Each of them carries 1 flux quantum. And the system is described by the so-called Sine-Gordon model, more exactly perturb Sine-Gordon model. I will mention it a little later. But in general, this is the equation which is known in various areas of physics. This equation actually for Josephson junctions was written by Farrell and Brage back in the 60s, shortly after the discovery of Josephson effect. So phi is the phase difference across the barrier of the Josephson junction, which depends, as I said, both on time and coordinate. So this phi is actually a function of time and coordinate. And if you now set the time to be constant, you just want to look into the solution of the stationary equation, which is a nonlinear ordinary differential equation of the second order, then the equation has solution in the form of a kink. So if you plot here vertically the phase difference of the junction, find the right way of working with this pointer. So this is the phase, okay, this is the energy, this is the phase difference across the junction, and this is the coordinate. So basically, the phase difference can change over 2 pi at a spatial scale, which is smaller than the whole length of the junction. So in some part of the junction, the phase is 0. In some other part of the junction, the phase is equal to pi or minus pi. And this is actually the topological soliton, a kink, which is, of course, also kink in the Franklin contour model, which is the discrete version of the same equation. So this kink has actually exact analytical solution. So this equation is integrable, and the stationary form of this solution is given. This equation is given here. And then this is the exact solution, so you can substitute this function for arctangents of the exponent into the equation, and you find the solution is exact. Now, this solution located at the point x0, which is indicated by this dashed line on the plot, on this dashed line. Now, this solution corresponds to the object, which is generally for the equations called the soliton or a kink. And in terms of Josephson junction, it's often called a flux, and sometimes Josephson vortex. Why so? As I mentioned, the solution has a step extending over the length lambda j, which is characteristic length scale of the equation. And the step has a magnitude of 2 pi, and this is a kink. Now, if I take a spatial derivative of the phase difference, this gives me exactly the local magnetic field in the junction. This local magnetic field has a form of a localized kind of pulse or localized area. So if you integrate the magnetic field as a function of coordinate, then you will see that actually the integral is equal to exactly 2 pi, which is in physical units is exactly 1 flux quantum, which is Planck's constant divided by y is the electron charge. Superconducting flux quantum. And
I'm sorry, can I ask you a question? The magnetic field you applied here lies in the y direction. Which direction you apply?
It's a direction along this dashed line. It's in the plane of the vector. So, and you don't have to apply this magnetic field. Actually, you can notice that magnetic field at the boundaries, exactly here and there, is 0. But nevertheless, this Fluxon solution already exists. It's a question, of course, it may be not stable solution. It may be not easy to prepare it in reality.
You mean this the fluxon existed even after turning off the magnetic field?
Yes. Can exist at 0 magnetic field, external magnetic field, but it carries its own magnetic moment due to the magnetic flux penetrating superconducting barrier.
I see.
More easy is to imagine it's quantized flux quantum. In this simple system, this fluxon is always 2 pi. Yeah, there are some other exotic operations, like double sign Gordon and so forth, but this is a plain sign Gordon, so the solution is 2 pi volts, which corresponds to 1 magnetic flux quantum H divided by 2. Okay. Now, this fluxon is actually formed by superconducting currents, which are flowing around a small area. And as you know, currents across the Josephson junction, they are given by the Josephson, first Josephson relation. It's a sign of the phase difference phi. And if you take a sign of this solution, then you'll see that actually the sign of this step function is shown here. This is first positive current. The current is flowing upwards. Then it goes through 0. There is no current flowing across the barrier in the center of the vortex. And then the current is flowing backwards. Now flows from top to bottom. So this current actually is generating this magnetic field, and this current is called actually, it gives the name of this object also Josephson vortex. So it has an extension of characteristic lengths of this equation, which is the Josephson penetration depth, which is typically in the range of a few microns or a few tenths of microns. And this picture is not to scale because the vertical extension of the vortex is only twice the London penetration depth, which is typically smaller than micron, maybe about 100 nanometers. The thickness of the barrier is very thin; it's in the order of a nanometer. So basically, these currents are extending in the superconductor much farther away than the area of the barrier. Now, you can take the derivative of this equation. You have exact expression for magnetic field. You can take the integral, as I said, it's exactly 1/4. So this is, of course, all well known and described in many books. This is a standard kind of superconducting object. The interesting feature of that, which I want to mention, is that these objects, magnetic flux quanta in Josephson junctions and long Josephson junctions, they behave as particles or quasi-particles because they preserve their shape, and they have they can move ballistically in the presence of very small loss, which is typically the case in the Josephson tunnel junction. And they also show a beautiful phenomenon, which is the phenomenon known from special theory of relativity. This is basically the Lorentz invariance. So if I consider now time being present, there is exact solution for the full Sine-Gordon equation containing time. This is a moving kink, moving soliton with velocity vt. Now, a soliton of the opposite polarity can also be described by this similar solution. And both these solutions, they are Lorentz invariant. So if you replace x by this, to make this transformation, then basically you see that the equation is fulfilled. So basically, the spatial extension of the vortex, this lambda j, is only lambda j in the static case. But if you move the vortex with the velocity close to the velocity of light in the barrier, then the vortex Lorentz contracts, and with a very large velocity, is just contracts ideally to zero. Of course, it doesn't happen because then the non-local limit will be met. You cannot really apply this equation.
The velocity normalized by speed of light.
Yes. This is the velocity of light in the junction. Now, this velocity of light in the junction V is the normalized velocity.
Normalized
to the velocity of light in the junction. So the velocity of light in the junction is called Swihart velocity or Swihart velocity, and it's typically roughly 30 times smaller than the velocity of light in vacuum.
How many times?
30. The reason is that the extension of electric field is very small and magnetic field is very large, and therefore you get renormalize the wave equation for electromagnetic waves. Now, in reality, this equation, which is now written in notation, the sub-indices are partial derivatives. It contains also perturbation terms. So perturbation terms are corresponding to losses, and they are due to the tunneling of quasi-particles, which is this term, and the tunneling also of the and the loss also due to the surface currents in the superconductor.
So this deformation break the Lorentz covariance, so the solution is not covariant.
That's correct. But good news are that this both alpha, beta, and gamma, they can be made very small. So one can really apply very consistent perturbation theory, which was developed in the end of 70s by McLaughlin and Scott. And this perturbation theory really describes the properties of this junction to a great degree of detail. Now, this equation, though it describes motion of flux quanta, it's fully classical equation. There is nothing quantum in this equation. It's only, we only know that the flux current is flux quantum, but if I take this equation and calculate what will be effective uncertainty in space for this object, we come to conclusion that the uncertainty in space is much, much smaller than the size of the solution. So it's really classical object, bulky classical object having a typical size of the order of u square microns. Now, these Josephson vortices, these fluxes, they have been studied in the 80s and 70s. 70s not in theory, but only theory. But then experiments came about in the 80s and also in 90s, where the phenomena like motion of this flux quanta, the Lorentz contraction has been studied, and people also understood that they really behave as solitons, like textbook solitons. One can really use this as a object to study the properties of solutions. Now, there have been also applications suggested and developed also devices where these fluxes were used in microwave and millimeter wave oscillators. For example, for radio astronomy, there was a beautiful, very systematic work done in Moscow by Valery Kocheles and his group, to combine this kind of oscillators with SAS mixers on the same chip and hereby implement millimeter wave integrated receivers. Now, these are all sort of old story, which didn't receive much continuation in the last 2 decades. Now, what was interesting, it was actually a question which once my PhD advisor asked me, Daniel Schmidt, Russian Schmidt, who wrote a book about superconductivity. Can the vortex can it be actually considered as a quantum particle? And the answer to that is that you have to basically reduce the effective mass of the vortex. So as for any quantum object, reducing the mass moves the system closer to the quantum limit. And if you calculate the effective mass of the vortex, then for typical parameters, is in the range of 10 to minus 3, or 10 to minus 4 of free electron mass. So it's a huge object, which has really tiny effective mass. And therefore, quantum effects are, we are sure now, within reach. What one can do here, the way to get to the quantum regime is basically to play with two non-commuting variables in a Josephson junction. These variables are phase difference and the number of charges on the electron. So there are two energy scales. The phase difference is given by the energy scale, which is the Josephson energy, let's say in the range of the vortex. And the charging energy is basically the electron charge or Cooper charge squared divided by capacitance. So if you decrease the capacitance, then the charging energy is increasing, and therefore the non-commuting phase and charge variables will really bring the system into the quantum regime. So the quantumness parameter, or if you want the effective Planck's constant of the system, is given by this ratio. And it's easy to notice that this ratio increases EC to EG, charging energy to the Josephson energy. It increases if the width of the junction is decreasing. So if you decrease the width of the junction, then basically the capacitance, capacitive contribution, the charging energy goes up, while the Josephson energy goes down.
Can I ask you a question?
Yes.
So is it maybe correct also to say that since a vertex implies that you have these ring currents there,
Yeah.
In which a certain number of Cooper pairs must participate,
Yes.
then it's this number of Cooper pairs which becomes smaller and smaller, so that you finally get into some kind of quantum regime where you start to see discreteness of these.
It's a good way of thinking of this. I would agree. So basically, this was the notice we had already back 20 years ago. And my that time former PhD student, Andreas Valerov, did this experiment, which we published in 2003, where we tried to reduce the width of the junction in order to observe quantum effects. So we took a Josephson junction, a long Josephson junction in the shape of a ring, and then we made this ring that time rather narrow, 0.5 micron. This was niobium junction. And then we did the experiment which mimicked the mechanical analog of the Josephson. What we did that time, we wanted to form a potential well for the fluxon, and then look for the escape of a fluxon from the potential well under the effect of quantum fluctuations. And to do this, we had a fluxon trapped in this ring-shaped junction. Okay, this is a fluxon with some magnetic moment. And we applied the magnetic field in the plane of this ring. If you do that, then this magnetic moment has the lowest energy when it's sitting along the field, and has the highest energy when it's facing against the field. So one can easily notice that in the absence of the bias current, the potential for the vortex becomes cosine-like. Okay? And the amplitude of the cosine is proportional to the magnitude of the magnetic field which you apply. And then by applying a bias current, by sending a current from top to bottom of the field, you can tune this cosine potential very, very similar to the model we have for a virtual particle for Josephson junctions. So basically, instead of the phase coordinate, which we have in the textbook for Josephson junction, you have here a real special coordinate if you want the angle of the position of this flux. And the flux sitting in this metastable well here can escape from this metastable well. So there will be switching of the current from 0 voltage state to the finite voltage state, if this happens, either by thermal escape over the barrier or by quantum tunneling. And in that work, actually, we observed a transition from thermal escape to the quantum escape. The data are shown here. So we were able to measure down to millikelvin temperatures the standard deviation of the measured critical current of the junction at different magnetic fields, which means at different barrier heights. And then we made sure that actually the saturation which we observe at low temperatures at different magnetic fields is not due to some noise in the experiment, which of course will also make some standard deviation of the data, but actually was depending on the field which we applied, which allows us at that time to conclude that the saturation is due to the crossover from thermal fluctuation regime to the quantum tunneling. And as you may know, observation of quantum tunneling in Josephson junctions has been done already in the middle of '80s by the group of John Clark, measuring the escape from the superconducting state for a tunnel junction. And about the same time, his team, including John Martinez, Michel Devaret, and Esther Urbina, and so forth, they were able also to observe for the first time energy level quantization in the potential way.
So can I ask you some experiment? I wonder, can you have any experimental evidence about how many fluxons that are in this Josephson junction and where the location?
It's moving free. This fluxon is moving free.
Yes.
It has a very small PD. We know this from the critical current of the junction. If you don't apply any DC magnetic field here, then this junction has a very tiny critical current, almost zero critical current. And as soon as you apply this bias current, the fluxon starts rotating. And you can nicely measure this relativistic current voltage characteristic, which we have done, of course, multiple times.
Then in the experiment, can you observe, for example, the step-like features that depending on the number of fluxons?
Exactly. This is exactly what was studied even before this work.
Thank you.
So now in this experiment, which now let me come back to this to the history. So these observations in the middle of '80s of macroscopic quantum tunneling and energy level quantization, they were predicted by Tony Leggett and also independently by Larkin and Ovchinnikov at the end of '70s. And for 20 years, there was not much progress. And then in the beginning of 2000, this all evolved into the flourishing superconducting qubits and quantum computing, which we all know about now. Now, in our experiment, we have done, we think for the first time, we have shown here 20 years ago, tunneling of a macroscopic object, which has a spatial structure in real space. And also we did microscopy, and we were able to map energy levels of fluxons in this potential, and the agreement with theory was very good. So, but we have not obtained any notes, any signature of the coherence. So the coherence means that in the system we would expect a superposition of macroscopically distinct spatial states. In usual Josephson junction, you have the coherence between current states, like clockwise current and counterclockwise current. These are superconducting qubits, which of course form two-level system and so forth. In this situation here, basically we were only able to achieve the result which was achieved already almost 20 years ago with point-like junction, but not with extended optics. And remains still an open question, how to make the junction more quantum to make this behavior more spectacular, and how to make the experiment which would unambiguously show the existence of superposition of spatially distinct phase distributions in the junction. So this is basically superposition of two string states, if you want, in the Sandborn model.
What happens when your vortex tunnels out? What is the new state then it tunnels into?
It tunnels out because the dissipation is small, and I have a tilted washboard. It just runs down the washboard forever, and I observe voltage.
You basically lose it.
We lose it. We have to start the experiment again.
So you need, so to say, final state which is as well defined.
Yeah, but you see, this data, each point is 10,000 averages of repeating the experiment 10,000 times and measuring the standard deviation.
You're talking about coherent, macroscopic tunneling.
Yeah.
And tunneling itself is already quantum phenomenon.
Yes.
And coherence is additional quantum phenomenon.
Exactly.
What you mean by this coherent tunneling?
Well, for how long time the quantum state exists? For how long time the superposition survives? We know that in superconducting qubits, this time can be a fraction of milliseconds.
But if you have initially superposition and you want it to tunnel, yes, and how?
If I form a superposition, for how long time the initial state can exist in the prepared quantum state? If you, I'll come to that in a second.
So if that also a question about a theoretical question about the Sandborn model, the model you mentioned, as far as I know, has the solution for a single flux state. So the model can describe the multiple fluxons.
Yeah, of course.
I see.
If they don't overlap, then
don't overlap.
The solution of sum of many fluxons is also solution of the whole equation. If they overlap, there are also other solutions like breathers and so forth.
I see.
Okay, so let us look closer. What means this ratio for EC over AG? Actually, this is proportional to the wave impedance of this long Josephson junction, which is basically proportional to the square root of the inductance divided by capacitance per unit length. And I already said that it's proportional to 1 over the width. This is correct. But also there are two other parameters to play: the inductance and the capacitance. Now, if I simply want to reduce, for example, the Josephson energy here, to increase this quantumness parameter, this effective Planck's constant, then I come to the problem, because reducing the Josephson energy, if I cannot reduce the width anymore, reducing the Josephson energy requires reducing the critical current density. And this in turn makes the Josephson penetration depths become larger and larger and larger. So my vortex size becomes larger than the junction. I cannot do anything anymore. So I cannot really play with the critical current here. However, I can play with something else, and I can play with inductance and capacitance. Now, capacitance is very difficult to change because it's basically determined by the thickness of the oxide barrier. It also determines the critical current density, which determines in turn the Josephson penetration depths. So the most interesting parameter is the inductance. And if I look into the history, first theoretical paper discussing long junctions and actually quantum behavior of vortices, to my knowledge, was this paper by Kato and Imada back in the 90s. This was just theory. Then in our experiment, which I already just reviewed by Andreas Valerov and authors, we went to the year 2003. We had this quantumness parameter getting closer to 10 to minus 2. And there was a follow-up experiment of my PhD student, not much published of that, but he made it a bit better, but not really increasing by order of magnitude. Pay attention, this is a logarithmic scale. So this is a logarithmic scale for this effective normalized Planck's constant. Now, and the way here to go is to use a different material to make the inductance larger. And the solution is basically to add a kinetic inductance. Kinetic inductance can be increased by choosing, instead of conventional superconductor like niobium or aluminum, choosing a disordered superconductor. Now, kinetic inductance in superconductivity is well-known notation, can be really large in superconductors which are made of disordered metals. For example, niobium nitride, niobium titanium nitride, and many others. And in our experiment, which I'm going to show in the next, we actually were able to make a step larger than 1 order of magnitude. So we went from 10 to minus 2 to almost 10 to minus 3. And we did that by choosing a superconductor, which is actually different from conventional ones. We choose granular aluminum. Conventional aluminum, you know, has a critical temperature of 1.2 Kelvin, and it's a very good metal. And it's a typical material which is used for superconducting qubits. So it's like a silicon of superconducting electronics for quantum computing.
Sorry, that one question, but in the previous slide, although your junction is in the short length limit, I guess you see some similar physics still in this short junction. There are vortices, Josephson vortices. So the long Josephson junction, the long length L compared to the penetration depth is essential in your.
So this length, in my case, what I'm interested is actually in the situation when this length is larger than the Josephson penetration depth.
Yeah,
this is the case I'm considering.
Yeah,
of course, you can apply very large magnetic field to any Josephson junction, you will get the vortices, but they will not behave as solitons because they will be simply a solution of the linear function.
Yes,
sum of the linear function.
Yes.
This is, of course, not having any relevance in that context. So I'm looking into the states with weakly overlapping Josephson vortices.
You mean this linear region of the phase variation as a function of the length? You see the significant overlap between the vortex states.
I will show. Maybe we could discuss it in one of the next slides when I show the Fraunhofer pattern and show the difference between the lamp Josephson junction, short Josephson junction, small and Josephson penetration depths, and long junction.
Yes,
it will be appropriate to come back to that a bit later. Okay, back to granular aluminum. So granular aluminum can be made by sputtering aluminum in vacuum with some significant residual pressure of oxygen. In this case, aluminum gets oxidized while being deposited, and it forms a kind of granular structure with the size of the grain about 3 to 4 nanometers. The surface are pure aluminum grains, and you could see from order of aluminum actually inside the grain. And between the grains, there is a aluminum oxide, non-stoichiometric aluminum oxide, which plays the role of a tunnel barrier. So basically, you have grains which are weakly overlapping with each other, and between them, there is always tunnel barrier, which actually makes this kind of a granular medium very similar to an array, three-dimensional array of Josephson junctions. So you have many, many grains, all connected by Josephson coupled. Now, there are many mysteries about granular aluminum, because if you, for example, take single particle quantization condition for 4 nanometer grain, then the energy difference between the levels of a single particle quantization will be larger than the superconducting gap. So this material can only superconduct when you have a significant overlap of the wave functions of the condensated different grains. And there are also some mysteries, like, for example, the critical temperature of granular aluminum goes up to sometimes more than 2 Kelvin, and then drops down closer to the superconductor to insulator transition. So depending on the amount of oxygen, you can go from pure aluminum to highly disordered superconductor, and if you add even more oxygen during deposition, then you are basically in the isolating state. So this is kind of also interesting material, interesting system to study the superconductor to insulator transition. But I'm not talking about that. So we started this work back more than 5 years ago. And this is a picture taken in the transmission of the microscopy. Basically, this granular aluminum is a convenient source of introducing additional inductance. And this is also relevant for the field of, for example, superconducting qubits, because if you add the inductance, kinetic inductance, which can be 2, sometimes 3 orders of magnitude larger than the geometrical inductance, you can make the footprint of circuits much smaller. And actually, this helps to simplify the design of superconducting components. Now, the kinetic inductance has a mechanism that if you have a low density of Cooper pairs, then by sending a current through this superconductor, the Cooper pairs, they are required to gain a significant kinetic energy, which actually has the same role as the kinetic energy of the currents in the coil. The geometrical inductance doesn't generate magnetic field, while the kinetic inductance, of course, does not generate any cell field and is existing there simply because of the kinetic energy of moving Cooper pairs. So this is now the structure which I want to show first. We did this long junctions with granular aluminum first to understand what will be the properties of the long Josephson junctions. So we made basically top electrode, the bottom electrode, and then we made a junction in this area. And then in this particular experiments, we had a barrier on both sides was granular aluminum. And here this kink is basically when we make aluminum oxide barrier between the layers. So this is the deposition of pure aluminum. And then here we increase the pressure of oxygen and wait for some time until the barrier is formed, and then we continue our deposition. We were able to prepare these films having in situ control of the resistance of the films, and then we're able to really do by oxygen adjustment to come to the specific value of the kinetic inductance that we want.
I wonder what is critical temperature of this granular aluminum in an experiment?
It's typically will be close to 2 Kelvin.
Okay, it's significantly lower than bulk aluminum.
No, higher. Higher. For aluminum, this is a mystery, which I mentioned. In granular aluminum, the critical temperature increases with increasing disorder. And then it starts dropping when you get close to the superconducting insulator transmission. So this story, this is not well understood.
Large charging effect should kill superconductivity.
At the end, yes. But before that, it's really increases, and people have seen it many, many times.
Yeah, it's probably the surface.
Yeah. So now this is a pattern, the measurements of the critical current versus magnetic field. This is zero current, zero field, and this is positive field, this is negative field. Now you notice immediately this asymmetric shape of the central peak here. This is due to the asymmetry of the current injection in the junction. So basically the critical current is not symmetric because we were injecting the current on the one end of this long junction. Now, skipping the details, this is the paper which I published, which only partial relation to my talk today. I show this slide for the reason that from these measurements, we are able, from the critical field, we are able to calculate what is the Josephson penetration depth. And we find out actually that the Josephson penetration depth has been reduced by a factor of almost 40 here, which corresponds to the factor of 40 square increase in the kinetic inductance. So basically, in spite of the low critical current density, the size of the vortex has shrunk very significantly. And this actually helps us to get this large kinetic inductance, which we need also for the quantum wavelengths. We also did measurements of the motion of individual solitons in this junction, and these are the data taken for a zero magnetic field. You see this state of oscillating one vortex can hit here, reverse the polarity, then hit there, reverse the polarity, and just shuttle-like motion of the vortex. It has moving like a vortex in this direction and anti-vortex after reflection in that direction. This is a well-known phenomenon observed already in the 70s by Fulton and Dines in Bell Labs, and then it started in many experiments in the 80s. So
I'm sorry, about the size of the vortex, the the previous slide, you said that this the penetration depth that reduce the penetration depth that determines the size of the vortex. In this case, the superconducting coherence strength doesn't play any role in the shape of this.
Superconducting coherence length doesn't play any role here because it's all magnetic vortex that doesn't have any core. So it's singularity sitting in the barrier. We know that coherence length is actually comparable here with the size of the grain, but it plays no role here.
The core you mentioned is different from this X0. When you explain this the sign equations, I thought that X0 probably the position of the vortex and the core of the vortex, but it does not mean the core of the vortex.
There is always a singularity in the tunnel barrier, which you go around and you get the change of the 2 pi. And this singularity is existing also in abricosal vortices.
Yes.
And then it's actually within this coherence length at the core.
Yeah.
But since the vortex is Josephson vortex, it doesn't require any core. So basically the order parameter is not suppressed at all.
I see. I see. Yeah. Thank you.
Okay, so we see here the voltages of the zero field steps. We know the length of the junction. From that, we can measure the velocity of light in the junction from the asymptotic value of this step from this voltage. This is twice the same voltage, and this is 3 times the same voltage. We can also verify these positions of the step by applying a magnetic field. In this case, they're appearing also half integer steps at half the voltage and 1.5 the voltage and 2.5 the voltage. These are these steps in magnetic field. And from that, we can calculate exactly from this data what is the velocity of light in the junction. And we find it to be of the order of 3⁻³ of the velocity of light in vacuum, which is, from our measurements, 25 times smaller than the velocity of the spherical velocity in pure aluminum junction. So basically, these vortices, they move now much slower in the material with kinetic inductance than they move in materials from pure aluminum. And this also corresponds to the significantly increased junction impedance, which may help also, for example, for matching these long junctions to conventional 50 ohm microwave circuits. But that's another story. Now, the message here is that the Josephson penetration depth decreases, and the velocity, spherical velocity, also significantly decreases. And this kind of junctions, we decided now to use to observe the coherence between spatially distinct states.
Could I ask you, if you put current along the tunnel barrier, so this current should push this vortex to move?
No.
It's pinned by edges, or I mean, it's a Lorentz force. And
yeah, but we apply the current is connected to 2 different electrodes.
Mm.
So in this case, the current distributes itself across the Josephson barrier over some distance, typically the penetration depths.
But if you put another current parallel to
This has the same effect as magnetic field. This is purely applying a DC magnetic field in the grid. One can apply current, or one can apply magnetic field. Doesn't make much difference. Because that current.
Bulk materials, if you have vortex system and you put transport current, you push vortex system.
Yeah, exactly here. So the current, in our case, moving from flowing from top to bottom, it exerts a Lorentz force acting in perpendicular direction. And this Lorentz force acts to the right for the vortex. When it reflects into anti-vortex, acts to the left.
So reflection is important.
Yeah, reflection is important.
It's spin.
Yeah, because you need to satisfy the boundary condition magnetic field equal to 0. And this can be only satisfied if you consider a virtual anti-vortex, which is moving simultaneously on the other side. And so when the vortex disappears, the anti-vortex enters. And by that, you satisfy the boundary condition d phi over dx is equal to 0. All right.
Which means what? That there is no, that the static solution, you started the whole story with, doesn't exist in your experiments.
Yes, because
It will start moving, right?
yeah. So the vortex sitting there is unstable, and if you apply very weak current, it will simply move and annihilate. But if it has significant kinetic energy, this energy cannot be dissipated.
But if you don't apply any current, then it would just be static, right?
The static solution exists in the case of, for example, a ring periodic boundary condition, which I showed in previous experiments. But here we have open end, so it's not stable.
But if you consider this is a quantum object, so you have to introduce a probability, and then it should be smashed from one side to another side.
Exactly. Yeah, but this is not the quantum story. This is all classical story so far. I'm coming to the quantum now. Now, to make the system behave quantum mechanically, of course, we try to reduce the effects of the coherence. And when we apply current and measure the voltage, we dissipate a lot of energy. This energy stays there in the junction. So basically, this is the way which doesn't work to observe quantum phenomenon. Now, what we have done for that, to observe quantum phenomena, we did the following. We made a structure which is schematically shown here. This is a cross-section of the circuit which is made on the sapphire. We have a feed line which is used here. This is a side view. We send the current in this feed line, microwave current in this direction. So here it goes from low end to the high end. And then capacitively coupled to this feed line, where we send the microwave, capacitively coupled, we have a half wavelength open end resonator made of a superconducting granular aluminum. So this is the structure which you show there, which you see there. And then we, on this piece of superconducting, which is not connected to anything else, has only capacitive coupling to this feed line, we deposit a piece of aluminum. So one electrode of the junction is going to be just aluminum. We did it for convenience. And the other electrode is the granular aluminum. Okay, we lose some kinetic inductance. Actually, we lose factor of square root of 2 in the velocity of light, but it doesn't make much difference. So basically, this is going to be our resonator, which we couple to the microwave line. And this is going to be our junction, which we have galvanically coupled to this resonator. Now, in superconducting qubits, the standard technology of measuring the state of a qubit is the so-called dispersion readout. In this case, you have a resonator which is coupled to some transmission line, and then you observe this resonator as a dip in the transmission. So the frequency of the resonator, the microwave will be reflected from this resonator, and therefore you have lower transmission.
Is the coupler waveguide structure?
This is a coupler. No, this is not the coupler. This is step line. Actually, it's actually free hanging strip. So we use some for the feed line. We use some back plane on the other side of the substrate, but it's not very important. Just to bring the impedance close to 50 ohm. Now, if you have a superconducting qubit, which is inductively or capacitively coupled to the harmonic oscillator, to the resonator, then superconducting qubit, which is getting excited from the ground state to the excited state, the superconducting qubit is coupled to the resonator, and it can shift the frequency of the resonator very slightly. So basically, the resonator frequency is very different from the frequency of the transition in the qubit. However, if the qubit goes from ground state to the excited state, then the resonator frequency shifts. And this is the dispersive readout, which has been first invented for measuring atoms, and then was reinvented for superconducting circuits. Actually, by very same Andreas Vallerov, who did the first work, and he did this circuit QED experiments in Yale a few years later as a postdoc. Now, basically, we have the current which will flow in the resonator, and this current will flow partially through the bottom electrode and partially through the junction. So it will be coupling the junction to the resonator. And then in this resonator will have different nodes. So the fundamental node is half wavelengths. We will get for the antinode in the region of the junction. The second mode is not going to be coupled strongly to the junction because it will have a node exactly in the middle. And basically it's similar to the situation which Serge Harosh, Nobel Prize winner 2012, has been using for Rydberg atoms actually in microwave cavity to measure the state of Rydberg atom being excited or de-excited from the ground state. Now we are measuring the basically the dip of the transmission in the spectrum of the microwave line, and then when we excite the transition in the circuit which is coupled to the resonator, we can observe a little shift of the frequency of the resonance. So this can be.
Professor Ustinov, we have a question from online. Professor Inkin Goldman.
Yeah, I think I missed you. What is the benefit of using granular aluminum?
To have large kinetic inductance. Granular aluminum is a material which makes it possible to achieve kinetic inductance factor of 100 to 1,000 larger than geometrical inductance.
Okay, thank you. Thank you.
Okay, so basically, this is our geometry. We made by purpose now this long junction actually very narrow, and it looks like shown here. So this is now a picture in its scanning electron microscope of this lambda half resonator. And then this dark blue line is the long junction, which is lying on top of the resonator. It has the width of only 200 nanometers, 0.2 micron, and the length about 90 microns. And then we measure as a function of the magnetic field in the plane, we measure the properties of this resonator. We measure the position of the resonance of the resonator. Okay? So, and what we observe is the following. If you have no Josephson junction on top of the resonator, then applying magnetic field in the plane slightly reduces the frequency of the resonator. You see this is a very small reduction of only about 1% of the resonance. So the dark color is a dip in the transmission. And this is due to the reduction of the density of Hoover-Peterson magnetic field. So basically you have a small dependence on magnetic field. And if you have no Josephson junction on top of the resonator, we have verified that, then this line, this dark line, has nothing particular, it just has no features like shown here. Now, if you have a long junction, then there are very spectacular features appearing here. You observe here some feature, you observe there a feature, you observe also here a feature. And if you zoom in and then scan in detail the point by point at different frequencies, the transmission around those features, then they look like this. They look exactly like avoided level crossings of two-level system with a resonator. So you see here, there is a line going, show here. There is some line going from top, now down, then it has some minimum, and then it comes back going upwards. Very similar pictures are observed if you couple, for example, flux qubit to a resonator, and then you change magnetic field, which you apply to the flux qubit. And then if the flux qubit minimum frequency is below the frequency of the resonator, then you will have two avoided level crossings looking very symmetric. So by fitting these avoided level crossings to the spectrum of hyperbola, which is a characteristic spectrum shape of a two-level system, one will be able to find the lowest frequency of the flux qubit, which is occurring at the magnetic flux applied to the flux qubit equal to half flux quantum. So these are the features which we observe. Now, what is the interpretation of these features? I'm coming back to the question you had about short junction. If you have a short Josephson junction, much smaller than the Josephson penetration depths, then the picture is this textbook Fraunhofer pattern, which is simply, you have, of course, a vortex here and then two vortices there, but these vortices are simply corresponding to the linear solution of the phase. So the phase is equal to linear function of the coordinate.
Yes.
If you have a long Josephson junction, then very sketchy, the picture looks like this. If you apply magnetic field, then at first the junction is screening away the external field. So the critical current is only reduced nearly linearly. Actually, the exact solution for uniform biasing is not linear, But if you have the edge biasing, then it's exactly lethal. And then if you come to the critical field where the vortices can penetrate to the junction, then in infinitely large junction, the critical current is always zero. There will be no vortex states. So this is the first critical field, which I already shown to you in different symmetric shape, which actually tells me how large is the size of the vortex. Now, what we need to understand the data I showed, what we need to consider is the finite length of the junction. If you have something in between this behavior and that behavior, when the length is not very large, but let's say between 5 and 10 lambda j, then the picture looks like this. This is the critical current of hypothetic junction, which has a length, let's say, between 5 and 10 lambda j, or more exactly 7 to 8. And then the first critical field is somewhere here, but when you come close to the first critical field, there will be already a state with a single vortex competing with a state with no vortices. And each lobe here corresponds to the states with different number of fluxes inside. These fluxes, they weakly overlap. But for example, at this particular magnetic field, both solutions are possible with one vortex and with two vortices in the junction. So they have different depleting current depending on the magnetic field you apply. If you apply larger magnetic field, then the two vortex solution is more stable. If you apply a bit low magnetic field, then one vortex solution is more stable. But still, you are able to identify different states by measuring the critical current. This is a well-known thing, has been measured in Josephson junctions many times, and actually has been also seen in the data which I showed before. Now, what we observe that there is a critical current being equal to particular magnetic fields when two vortex configuration actually overlap. And the critical current, of course, is calculated when we tilt the whole system by applying the bias. So this is basically the deepening of different energy states. But we can sort of quantitatively rename it as minus energy, which means that the larger is the curve is the lower energy state it is. And at zero magnetic field, of course, you have no vortices, the lowest energy state. But then if you come to some higher field, then the zero vortex state coexists with the one vortex state. And then two vortex state coexists with one vortex state. And if you would allow for tunneling between one state and another, then exactly at this point, they will have equal energy. So basically the system will have two states separated by some barrier, and this would be behaving in a similar way as a conventional two-level system.
Excuse me, please. Length in which direction? This or this?
Length is in this direction on this plot.
This is, and what is this direction?
Now, this is the energy.
Okay, length. I understand. Yeah. So length is.
Yes. You see, you have this configuration and that configuration. And classically, you would say that this minimum corresponds to this configuration, this minimum corresponds to that configuration. Of course, you have to add the vortex inside. So you have to go from one configuration to another. So basically, the vortex penetrates into the junction. And this will have a certain barrier, which depends on the amount of magnetic field which you apply. But basically, if you have symmetric potential, which is the case exactly at the arrow here, then this epsilon is equal to 0, so you have exactly symmetric double well. And your equal energy states are degenerate, but in the presence of quantum tunneling, this degeneracy is lifted. And basically, you have the symmetric wave function and antisymmetric wave function with the energy difference. And what we measure actually in the spectrum, which I showed before, I will come to that again, is the energy difference between the ground state and the first excited state. And if the states are coherent, then we should be able to observe also the temporal coherence of the states. So we have done these measurements in detail, and actually to do the spectroscopy of the energy level separation as a function of this parameter epsilon, which is roughly proportional to the magnetic field, you need to do the two-tone spectroscopy. So you measure the frequency of the resonator by measuring the phase or the amplitude of the signal in the transmission line, which you have coupled to the resonator. And then you apply a second tone, which excites the qubit. And if the second tone hits the resonance frequency of the qubit, then the frequency of the resonator is shifted. And basically, this frequency, according to this two-level model, should depend hyperbolically on the asymmetry parameter epsilon, and we'll have this parameter delta, which is the tunneling amplitude in the symmetric well. And basically, this is our data. You see, the two-tone spectroscopy reveals this hyperbola very beautifully with the minimum frequency of the symmetric double wave potential being roughly twice lower than the frequency of the resonator. Of course, if the system, if the qubit has frequency close to the frequency of the resonator, then you will have this large dots, which are the rudiment kind of feature of the measurements. So basically, by fitting this two-tone spectroscopy data to the hyperbola, we can determine the tunneling amplitude between the states. Now, this is still work in progress, and we are working together with Mikhail Pistol, who I believe is known here, has been spending some time in the group on the model. The problem is that if we start from low field state, then the vortices overlap very weakly, and one can sort of make the model of them interacting in the exponential way. If you go to a bit higher fields, then of course the vortices overlap stronger, and then doing the analysis, actually applying the analysis of weakly interacting vortices is not eligible. So we do have now preliminary agreement for almost all the cosmos. And we could say that actually we see not only the states of crossing like this state, but also the higher order crossing, like crossing the second state with a zero order state, crossing the second state with the fourth order state, and so forth. So these are still work going in progress, but what we are sure is that actually the appearance of this this hyperbola in the two-level spectroscopy indicates superposition of the macroscopically distinct vortex states.
Can I ask one question? That the minimum of this parabola is the degeneracy point between the zero.
Exactly. Yeah, exactly. So this actually is depending on the height of the barrier.
Height of the barrier.
Yes.
The delta means the superconducting model.
It's a tunneling amplitude.
Tunneling amplitude.
But of course, this separation now, because epsilon is non-zero, is not exactly delta. It's given by the excuse me, by this formula.
I see.
So in this experiment, what tunneling occur here?
Vortex
Come from outside,
from outside going inside the junction.
and you can go outside preserving some quantum coherence in this configuration.
The vortex is simultaneously inside and outside.
Yes.
This is a weird thing. Okay, so basically we have done the measurements of the temporal coherence, and to do this we apply microwave pulses at the frequency of the transition in the qubit. And in the degeneracy point, we observe coherence, which is quite appreciable. We also verify that the Rabi frequency is proportional to the drive amplitude, as it should be for the two-level quantum system. And the coherence times were measured in the standard protocol. This is the measurements of the energy relaxation time. So basically, you apply a pi pulse, which is half the period of Rabi oscillations. And then you measure the population of the excited state. And then to measure the Ramsey dephasing time, you apply 2 pi over 2 pulses. And then if you want to cancel out for low frequency fluctuations, you apply also pi pulse in the middle, which is a scheme to measure the Han, all very well-known things for superconducting qubits, which we're also working on. So basically, our results are that the energy relaxation time for these superposition states is quite high, actually, for superconducting qubits. It's as large as 45 microseconds. Now, the free precession decay is limited to roughly 1 microsecond. We believe this is due to the fact that the magnetic field, outside magnetic field fluctuates. The fluctuations are mostly low frequency fluctuations. And we could see this when we put the pi pulse in the middle. We see that actually the echo time is roughly order of magnitude larger. So by doing that, we cancel out low frequency fluctuations. So this is basically a two-level system qubit, which is made in a single piece of material with a long Josephson junction between them. Now, this is, as I said, work in progress. We are working on full comparison with theory and have already preliminary rather good agreement for most of the crossings. I should repeat that we have done these experiments many, many times. So we pulled down more than 10 times, and we were always finding these crossings in the same position. So we are rather sure that this is not due to some bug in the setup. It's really, we saw it in two different samples in different ways. So I think what we observe now in the long junction is similar to what was observed by Nakamura and also by other co-authors, other people 20 years ago, when they observed temporal coherence in superconducting qubits. And about the same time, we were able to observe quantum tunneling in spatially extended system. And now basically we come to the conclusion that quantum superposition of spatially distinct vortex configuration is possible, and the coherence time is actually quite large and similar to superconducting qubits. So these devices can be also used for successful implementation of the Josephson vortex qubit, which can be rather compact qubit. It has quite high coherence times, and actually we think that pushing more the kinetic inductance contribution may lead to the case that the vortex will become an object for which the spatial uncertainty will become comparable with its size. And then it's a real quantum particle, which we could, of course, play with wave packet on the macroscopic scale. And maybe we could hope in the future to implement flying vortex qubits to transfer quantum information from one location to another. But that's something which is still being speculation. So with that, I will stop and thank you for your attention.
Thank you, Alexey.
Thank you very nice for this amazing topic. So it's really amazing to see what different times you have right now. I have two questions. First question is related to synchrotron spectroscopy. So could you please remind, I see many interactions, you explained us many interactions of the qubits with the resonator, right? Why do you see so many? Why don't you see only one? So they stay nearby each other.
Because we have different vortex states. So we have one overlapping with two, two with three, three with four, and also like one with three, and four with two. So we have multiple field level larger than the first critical field. We see many different configurations overlapping having the same energy.
And my second question is, so the experiment you showed here, is it with only one chip, or you tried also different chips? Because usually when we talk about quantum computing and its application, right? We talk about technology and it's how good is, how repeatable is it, and so on. So maybe you can tell us something.
We measured systematically two chips. We have seen it without more systematically on more than two, I think 3 or 4. We systematically measured two, and we see that it depends on the length of the junction. So really consistent with the station.
So your facilities, your facilities, it's quite reliable and repeatable.
Yeah.
Great, thank you.
Okay, more questions? Yes, Robert, please.
So you're measuring by this method, you're measuring dephasing and relaxation time here. And how can we be sure that it's intrinsic relaxation time, but not times caused by method of measurement?
Well, we are sure that, of course, there is always a contribution of the external interference, noises. And for an ideal two-level system, the degeneracy point, you would have T2 being twice T1. So you have T2, T1 limited. But we observe T2 here, even with echo, about a factor of almost 5 or 7 smaller than T1. So obviously we have some dephasing mechanisms which contribute there. And it requires a lot of effort, as we know from superconducting qubits, to come to the limitation that you will be T1 limited, to remove the origin of external dephasing. But what limits the T2, of course, the T1, excuse me, that's of course an interesting question. And partially it's limited also by coupling to the resonator with the Purcell effect, which is always there. But it depends on the crossing. Some of them have frequency closer to resonator, some of them not. So we need to study that. We did not do systematic measurements of that T1 for different crosses.
More questions?
I have one short question about this single tone spectroscopy data. Here, I guess the frequency shift you observed depends on the stage, either ground or excited. So in the experiment, you observed that.
No, the frequency shift occurs when we hit the transition frequency between the ground and excited state.
That's if I understand correctly, that's the two-tone.
Yes.
The single tone.
The single tone is the same, so we are close to that frequency. And then you have one frequency fixed, the other one is moving through.
Yeah.
Right. And then because you have the interacting two-partite quantum system, resonator, harmonic oscillator, and two-level system, you have avoided level crossing. So what we observe is avoided level crossing. This is a standard.
So the observation, the frequency shift you measured doesn't distinguish whether the states are in the ground or.
The frequency shift is when
I mean without the driving.
In the single tone spectroscopy, show this again. Yeah, in the single tone spectroscopy, you have instead of straight line here and straight line there, you have avoided level crossing. And this measures the coupling strengths between the junction and the resonator, which in our case is galvanic coupling.
I see.
Inductive coupling.
So it doesn't show any information. Sorry, I missed something there. I saw that in this case, the frequency shift has some information about your stage, whether it is in the ground stage or excited stage.
No, because when you have this line moving through, this line corresponds to a transition from the ground state to the excited state.
I see. I saw that you can also measure some stationary stage.
No. We measure always the transition between the ID states, the two-level system.
Thank you.
Yes, Boris. I have experimental question. So looking at the plot, it seems like you measured with hand, right? With hand semiconductor amplifier.
Yes.
Are you using like Josephson parametric amplifier?
Yes.
So
we use for this thing.
Do you have maybe some plots to see? It's interesting to see the difference compared to the difference.
Well, it's basically you need to have less variation. And here we use a traveling wave parametric amplifier.
Although you use a lot of isolators, of course, to reduce the effect from hand to your sample, let's say, right? So it's interesting if you have any change in the coherence time or the chain you have hand and you have JP. So
I think we didn't make a systematic comparison.
Okay.
We only saw that we can see much better contrast between the states.
Okay.
Our sheet is easier to measure. That's all.
Okay.
And we use the one which we didn't make. I got it from Vivo level.
Okay, sorry. On your picture, you show that the brain structure is quite irregular. Does it affect on the properties of junction, or it can increase property of junction? Or just make it regular.
It's probably very difficult to make it regular because this is a predisposition in the oxygen atmosphere. So the shades are getting crystallized they go down first. So I think making them regular will be a big challenge.
But does it affect on
the kinetic is not considered, but this hypothetically nobody made it regular.
Okay. Last call for questions. Forrest, excuse me. I have again very detailed experimental question. So continue with what Sergey asked about definitely you measured the physical currents of the junction in advance. I mean before you start. So how much is the spread of what?
Well, for long junctions, we don't really take this into account because average is over. So we have a really junction of the length of 90 microns. And we see that the signal current we observe is similar with the length of the junction.
Okay, if there are no more pressing questions, then still feel free to discuss with Alexey Ustinov later or Friday. Let's thank Alexey again for his collection. And tomorrow we have continuation with